All right, so we've got a quiz on Friday. There'll be a help session on Thursday, tomorrow night, at 7:30 p.m. on Google Meet. I'm also available today, sort of. I'm teaching lab from 2:20 to 5:20. So if after 3, let's say, after that, give me time to finish my lecture, if you wanted to stop by and you're a little bit patient, you could wait, let me, wave in the lab and then let me know. It's right above your Gen Chem lab is where I am. So if you wanted to come ask questions then, if you could wait a little bit, I could help. I'll have times I'll be able to come out and help you. Next week, we will not meet for lecture on Monday or Wednesday. Okay, I'm going to be at a conference for the American Chemical Society. There will be a quiz on Friday. It'll be on the stuff you learn next week. So what I'm going to do is, you may have noticed, actually it may not be learning, we'll see. But you may have noticed, if you watch the syllabus, that we had like a lecture or two ago, we were supposed to have practice acids and bases. I blew through that and cover more material. So that's going to be at least one of these days. I'm going to give you a worksheet, and I'll probably follow up with a video where I do a worked answer key of that worksheet. Okay. So, and then either both of these will be worksheets. We do have another worksheet day in there, or Friday will be. So I'm going to say it's not going to be stuff you learn next week, because there's not really going to be, unless I do an online lecture, there's not really going to be a lot of that. I'll probably give you a quiz on stuff that I hadn't quizzed on, that stuff we've covered already. All right, so we'll do that. We have lots of stuff in acids and bases, and now we're going on to buffers that we can use for that. Questions on what we're doing in the class? Yes?
Is there a chemical person?
I don't know. I think it's a poster session. I've seen poster session signs. Okay. So go to that, look at 3 posters, and write about them. Other questions? All right, then let's talk about buffers. So we've been talking about acids and bases, and one of the important parts with acids and bases is buffers. So buffers are solutions that resist changes in pH. All right, and they're made up of an acid and its conjugate base. Okay, both must be weak. Both must be at reasonable concentrations. Let's say reasonably high concentrations. And both must be at nearly the same concentration. And we're going to talk about why for all of these things today. All right, but if, anybody ever wants you to parrot what is a buffer, first off, what does it do? These are the most 2 important parts here, that it's going to resist changes in pH. That's what buffers are good for. Okay, and that's made up of an acid and its conjugate base. Your book has a slightly more complicated explanation, and we're just going to go with this one. This is the one that I've always used, this one right here, for what it's made up of, and that's worked just fine. Okay? Questions? All right. So here's a cartoon. I don't know if it's actually very useful, but it's just showing you the difference between if you have pure. So what's going on here is if I have pure water and I add some acid to it or add some base to it, I'm going to expect the pH to change pretty quickly. All right, so here they're adding enough base, acid or base that they're getting a 2-unit difference. So we're going from 7 down to 5, or from 7 up to about 9. That's what happens in pure water. If I was to take the same amount of acid or the same amount of base and I had a well-buffered solution, I would end up with a change that this is like a 0.12 change in pH, and this is also a 0.12 change in pH. So that's what we mean, that it's going to resist changes in pH. Buffers are really important in the lab when you want to do things. Lots of situations where you might care about what the pH is. You also care about, in nature, you care about the pH, right? We care about what the pH is of the ocean, okay? We care about the pH is of our blood. And both for the ocean and for our blood, we have the bicarbonate buffer system. I'm going to go with this aqueous. It's gas originally, but you can have dissolved carbon dioxide. Okay, whoops, sorry. That carbon dioxide can react with water to make carbonic acid. And that carbonic acid can dissociate to make H plus bicarbonate, which is baking soda. Okay, baking soda is sodium bicarbonate. Sodium isn't doing anything in it really.
Is that why they associate atmospheric CO2 increases to ocean acidification?
Yes, exactly. So that's why I'm going to repeat that. So you talk about we're putting more carbon dioxide in the atmosphere, right? And that makes the oceans more acidic. This is why, because if I put a bunch of carbon dioxide into the ocean, the equilibrium shifts this way, right? If I, Le Chatelier's principle, if I add this shifts this way and I get this, right? That's what's going on there. And so our oceans can take a certain amount of carbon dioxide, a certain amount of acidification, and at some point they stop buffering the atmosphere. They stop absorbing carbon dioxide because you've got too much carbon dioxide in. Okay, same sort of thing for your blood. Your blood uses the same system, okay? You produce carbon dioxide. So carbon dioxide we breathe in air, from the air is a fraction of some fraction of a percent, and the amount of carbon dioxide you breathe out is 4% of your air. Okay, so you're producing carbon dioxide in the process of metabolizing food. You make your food into carbon dioxide and water, and then you breathe out the carbon dioxide. Questions? Okay, so this is a little bit, it's an important buffer system, so I put the whole thing up. But we're not going to talk about things that have multiple equilibria like this. The important part of this, or the part that's most useful for us right now in this discussion, is just talking about the right part here. So that carbonic acid dissociating to make H plus bicarbonate, like that, okay? And so then this is our acid, right? And this is our conjugate base. And let's talk about how this works as a buffer. How does it resist changes in pH? All right, we're going to assume we have relatively equal concentrations of these two, and that they're high enough to actually absorb some amount of insult, amount of acid added or base added. We're going to use our Le Chatelier's principle again. We're going to use Le Chatelier's principle every darn time we can. Okay, super useful to think about. If this is at equilibrium and I add acid to it, what's going to happen? I add hydrochloric acid to it. Okay, so if I add hydrochloric acid, it fully dissociates. It's like adding H plus. And right, I saw a bunch of people point that we're going to shift the equilibrium this way. So if it's at equilibrium and I add some H plus, that H plus can react with the conjugate base to make more of this, right? So this is what pH is, right? pH is H plus. pH is negative log of H plus. So pH determines what pH is. We add some of this reacts with it and makes most of it go away. That's how it resists changes in pH. Does that make sense? Okay. How about the opposite way? Let's say I add OH minus somehow. I'm going to add sodium hydroxide, let's say, to that. Which of those things will that hydroxide react with up here? It's going to react with whatever's the strongest acid. What's the strongest acid? Remember this H3O plus? H3O plus is the strongest acid up there. All right. I'm going to go ahead and take that away. But let's go ahead and look at our previous notes. Right here. Where is H3O plus on here? It's just under the strong acids. Okay? So it's pretty strong. So if I add OH minus to this in some form, I add a strong base, it's going to react with the H plus, right, to make water. All right. Do you agree that if I add OH, it's the equivalent of reducing the amount of H plus? So if I reduce the amount of H plus, which way does this reaction shift? To the products, right? What's going on? I'm taking that away, so I need to make more. If I take this away, some of this dissociates to make more, to make up for the amount I took away. It'll make up for most of it. You see how that buffer works? With an acid and its conjugate base? Do you see that if I run out of this, I can't do this anymore? Right? So if I add acid and I add acid and I add acid, eventually I will run out. I think we got a molecular picture for that down here. Yeah, this is an example of that. So let's look at this picture for that. This buffer system is not the bicarbonate buffer system, which is the buffer system in your blood. This is a phosphate buffer system, which is one of the important buffer systems in your cells. All right, so it's going to maintain pH in your cells. If I have equal amounts of the acid and the conjugate base, that's great, I can buffer. Now we add some H plus, so we add some hydrochloric acid, let's say, and you will use up some of your conjugate base to absorb this, right? You're shifting based on Le Chatelier's principle. Then we can add some more H plus, and I can use up to this point where I have no more conjugate base left, right? Here I got a small drop in pH. Here I also got a small drop in pH because I could still absorb the stuff coming in. Here I don't have any more conjugate base to absorb it, and so now the pH drops a lot. Does that make sense? Why we have to have the acid and the conjugate base both around for a buffer to work. Okay. I said they have to also be at relatively high concentrations, which this kind of makes sense, right? What is relatively high? I don't expect you to know, but I can tell you from someone who's done lots and lots of lab work. My stuff now is computational, but I've done lots and lots of lab research in my time, and 10 millimolar buffer is not enough. So 0.01 molar buffer is not enough. You're probably going to get into trouble there. 50 millimolar, 0.05 millimolar is fine usually. Okay, that may or may not help, but what's a lot? What's enough? That's kind of the line I found. I don't know if you could find that in a textbook. I don't know if I've ever seen it, ever read that. That's more just something I found out. Okay, so what I want to do now is we want to demonstrate the buffer, but we're going to do a calculation here. This is something you guys know how to do, so I'm not even going to start it. But we have this reaction. Oh, no, hold on. We're not doing this one yet. We will do that one. Let's say instead of that one, though, we've got this reaction. H2Cl, ClO is an acid. It's not one of those strong chloride-containing acids. And that can dissociate to make HClO minus and H plus. And that has a Ka is equal to 3.0 times 10 to the negative 8th. I'm going to give you a problem here. It's going to be an ice table problem. What is the pH if the concentration of H2ClO is 0.40 molar? Okay, this is an ice table problem. Go ahead and take a few minutes and solve that. If you're not sure what to do, call me over. This is a great chance to practice your ice tables. Ice tables will be on your next test. I don't think, they weren't on your last quiz. Sorry, I haven't gone back yet. But I'll get that back to you before I leave. But they're not part of your last quiz, so gosh, I expect to see an ice table this Friday. Right? Yes?
Which one do you divide by which divide by 400 times?
Great question. So I've got a question about, I was going to go over this, but I'll go over it now. I've got a question about whether we can do our approximation and not use the quadratic formula. Remember that we set up our rule last time, that our rule is, so I got to find my pen, is 400 if you take the ratio of how much of your acid you have, okay? So the acid's the one on the left, it's the one with more protons attached to it, over your Ka. All right. And so if you look at these numbers, this thing is more than 1 million is what it's going to be, looking at those numbers, maybe tens of millions. So I can do my approximation where I assume that the amount of change is very small, whatever x is very small compared to this, so this could be my number. And that gets me out of having to do the quadratic.
It's your acid. It's the concentration of your acid.
Absolutely. Feel free to work together, talk to each other. Please call me over
Whatever
for questions.
acid is, that's what HA is. It's like H.
Give you another, hopefully you're at a point about to figure out your pH. I'll give you another minute. Okay, let's go ahead and work this one. So this is my equation. I'm going to do an ice table for it. right? We said up above that the concentration of the acid was 0.4 molar. So initial change equilibrium. 0.40 molar is that concentration, right? And then it doesn't tell me anything about the other ones. I have that concentration of acid, so I'm going to assume that my products are 0. All right. So which way is this reaction going to go if these are 0? It's going to go towards the 0. Always go towards the 0. You don't even have to have more than, you don't even have to have all zeros. If you have a 0, go that way. Okay. So then since we're going to go that direction, we're going to have some of our initial acid go away, right? It's going to dissociate, and it's going to become these two things. And for every acid that dissociates, I get one H3O minus and one H plus. I'm hoping, I was afraid that would happen. All right, I just wanted it to go away. Give me one moment here. All right, sorry about that. Okay, and so then after I have my equilibrium out, so I'm going to take the initial and I'm going to subtract the change from that, or add the change to that actually. So I'm going to go 0.40 molar minus X is what I get here, and I get 0 plus X and 0 plus X over here, right? But we decided that we could make the approximation, right, that gets us out of using the quadratic formula, that X is super small compared to 0.04 or 0.4, so we don't need to worry about it. All right, now we're out of having a quadratic. So I can, remember that K, 3.0 times 10 to the negative 8th? We can come down here, and we can say that our Ka is equal to products over reactants. Actually, I want to go up, we need to go up and see this. Products over reactants, our products are H3ClO minus and H plus. Okay, those are our products, and our reactants are H2ClO. Like that. Okay, and now I can just put the numbers in. My Ka was 3.0 times 10 to the negative 8th, and that's going to be equal to my products are both X, right? These are my products are both X, so I'm going to end up with X times X, or X squared. You okay with me doing that? And then I'm going to have my reactant is at 0.40 molar, because we made that simplifying approximation. To solve this, then, I'm going to multiply both sides by 0.40 to get my x's on the same side. All right, and if I put that into my calculator, you know, 3.0 times 0.4, so I get 1.2 times 10 to the negative 8th is equal to x squared, and then I'll press my square root button to get x. So x is equal to 1.09 times 10, oh, hold on. I was being lazy. 1, 2, 3, 4, 5, 6, 7, 8. 1.09, or 1 point, not. Oh, hold on. I'm sorry. Now, there it is. 0.00030 is 109. Okay? Or it looks like rounding 1. Okay? That's what X is, and that's equal to, remember, X was our product, right? It's the amount of this and the amount of this, H plus. And so that's equal to H plus. And remember, we're solving for pH, which is equal to the negative log of H plus concentration. All right, which is equal to, we'll just put in the numbers now, negative log of 0.000110. And I got 3.96. That what other people got? Okay. Questions on that? I'm going to make you do it again. Okay. All right. So now I'm going to change it up though. What is the pH? Now we're going to add some conjugate base. What is the pH if the concentration of H2ClO is 0.40 molar, just like it was before, and the concentration of HClO, that's our conjugate base, is 0.20 molar. Okay, I'm going to go ahead and give you some time to do that while I correct this, and I will rewrite the equation for you. Is there a question there?
Yeah, are you just like adding in the HClO minus?
I am. That's the concentration of both of those. Okay, so imagine you have water and you dump both these in. So, we're going to have the same chemical equation. I think I just heard somebody say that. But I will write it out here. It's this acid, whatever its name is, and remember your Ka hasn't changed here. It's 3.0 times 10 to the negative 8th. Let me give you one hint here. So we're going to put this in our equation. Is this, how does this compare to Ka? Is this more than 400 times bigger than that? Yeah, it's still like tens of millions. Okay, so you can make the simplified approximation for both. Other questions?
Actually, I do have a question. Does that look right?
That was about what it
Like,
was.
is that?
Yeah. That's what I remember.
Gotcha. So like this would be the sort of situation where the buffer isn't really doing its job because like there we have.
Well, it is doing its job.
It's just, it's actually doing its job, its PK is really close to this. We'll talk about it, but
Okay.
here it's doing its job, here we're not doing a job.
Oh, that's fair. Yeah.
Right, so this would be, because of the PK of this would be a buffer that would be good near 7.
Got it. Okay, that makes sense.
And I'll explain that.
Okay.
Another thing you think about is that the PK here is, you can take PK, it's going to be 7.05 or something.
Negative log
It's 7.5. So this pH is lower than the PK, and you have more of the acid than you have the base.
Oh, because you added the conjugate base, right?
You did, yes, but the ratio of the acid and conjugate base will determine.
So it's related to the pKa.
Right.
Got it. Okay.
Okay, let's go ahead and do this. So we're gonna do our ice table here. Initial, change, equilibrium. Okay, and so I'm going to start with 0.40 molar of the acid. I'm going to have 0.02 molar of the, well, not 0.02, 0.20, right? Molar of the conjugate base, and then I'm going to have 0 of my H+. Okay. Then I'm going to have my change. Which way do I go? This is confusing now because I've got this and this. Is this going to be a minus x or is it going to be a plus x? What was that? Towards the 0, right. It can't be a plus x because while some of this could turn into this, there's none of this to react with. Okay. So towards the 0. So this is going to have to be this. Some of this is going to go away to make one of these and one of these, right? Because that's the ratios from our equation. Now I can write my final then. My equilibrium concentration is HCl or whatever minus x. Here I've got 0.20 molar plus x, and here I have 0 plus x to make x. Okay. But remember, we said that we could apply our simplifying approximation to both the acid and the conjugate base because x is going to be really small compared to these numbers. And so now we have even easier math than we had last time because we don't have to do a square root. So our Ka is equal to 3.0 times 10 to the negative 8th. That's equal to products over reactants. So products over reactants. So are you guys okay if I don't write out the names of the products and then fill them in? Can I just write 0.20 molar times X? Those are my product concentrations right here. Over my reactant concentrations, which is just one reactant, it's that. All right, and so then what I'm going to do to solve this is I'm going to get all of my numbers on one side, my x on the other. So I will have to take this side and I will have to multiply by 4.04 molar over 0.20 molar, right? And that cancels with that, and that cancels with that. I did it to one side, so I have to do it to the other side. 0.4 molar, molar, 0.20 molar, like that. It's a little sloppy, so I'm going to go rewrite it 0.4 molar, 40 molar, 0.20 molar times 3.0 times 10 to the negative 8th is equal to x. And so 0.4 times 3 to the 8th divided by 0.2 equals, and I've got a 6 with a bunch of zeros in front of it. 1, 2, 3, 4, 5, 6, 7, 8. So I've got 6 times 10, 6.0 times 10 to the negative 8 is equal to x, which is equal to my H plus concentration. Remember, I was being asked about pH, so I need to figure out pH. pH is equal to the negative log of H plus is equal to the negative log of, in this case, 6.0 times 10 to the negative 8th, like that. And so I'll take my log and I get set pH is equal to 7.22. Is that what other people got? Okay, does that make sense? All right. Excuse me. Now, so we had to do two ice tables. First off, what's the difference here? When we just had this added to the solution, our pH was 3.96, right? And then when we had this, plus we had some of this, we had a buffer, right? Because we have the acid and its conjugate base, then we had a pH, let me do it like this. It's kind of a mess, but I'll do it. This is pH equals 3.96. And then this, when we had the buffer, was pH equals 7.22. Questions? You guys see how buffer works? All right, let's derive a new equation that will make it easier for us to calculate buffer, pH, pKs, things like that, without having to do the ice table. All right, be nice to not do the ice tables. But there will be an ice table on your quiz, I promise. Okay, so we're going to derive what's called the Henderson-Hasselbalch equation. Check and make sure I spell it right. Okay, I love this equation. First of all, it means I don't have to do ice tables anymore. Second, I'm just deriving it from there's these basic assumptions in chemistry, and then I do algebra, and I have this nice, useful equation that pops out. Okay, so once I've said this before in this class, that when we come up with these equations, they aren't magic. They're just usually taking something reasonable or some very basic assumption and then doing algebra at them. So that's what goes on here. If I have an acid-base reaction, let's say I have this acid dissociating, let's say acid dissociation reaction would be a better way of saying it, I'm going to end up with this. I'm doing this generic because we're going to be talking about, we're coming up with a generic equation for everything. So this is going to be the conjugate base, right? It is the conjugate base because it has one less H than the acid. That's how you can tell which is which in this kind of generic form. And then we know that we can set up a equilibrium expression for this. So I'd have the acid constant for whatever this reaction is, and it'd be products over reactants. Like that. Now I can take the negative log of both sides, right? I can do anything in algebra I want as long as I do it to both sides of the equation. So log of Ka is going to be equal to the negative log of Ka of, as a quantity, H plus over HA, like that. Okay? Now remember, actually I'm going to do it down here because I'll have more room. Now remember our log properties. If I take something, H plus times something else, so H plus times A minus over HA, think about those as two separate quantities. I'm multiplying this times this. If I multiply two things together inside of a log, I can pull them out and add the logs together. So this is the same as negative log of Ka is equal to negative log of H plus minus log of A minus over HA. All right. What is negative log of H plus? pH. What is negative log of Ka? pKa. Okay. Plus minus A plus, a minus is a minus, minus the log of A minus over HA. Okay, that's almost our Henderson-Hasselbalch equation. When they put it, we could use it just as it is. When they put it in books, they like to not have this, they like to have it solved for pH. So I'm going to go ahead, I'm going to add a log of A minus over HA to both sides. That's an HA. Okay, and when I do that, now I end up with pKa plus the log of A minus over HA is equal to pH. That's our equation. But usually they put the pH on the other side, right? I could do it like this. There's our equation. Questions? All right. Let's demonstrate how useful it is by having you do the next problem. You won't need to do an ice table here. The log is not negative because the question is, should the log still be negative? The log is not negative because what I did was I added plus log to both sides. Okay. All right. I want you to do this one. Okay. Henderson-Hasselbalch equation is not useful for these two. The reason it's not useful is here's the conjugate base, so that would go here. Here's the acid, so that would go there, but the other one's 0. Okay? So when one of them is 0, where it's going to diffuse, it's going to have some small concentration. You can't use it. But when you have a concentration of acid and conjugate base at reasonable concentrations, which you don't need to worry about, just assume if you have an acid and a conjugate base, it's good. You can use this Henderson-Hasselbalch equation. Call me over if you're stuck. I had a student last class who did really well on the last exam who called me over with questions, and he was calling me for questions. That means other people have questions. I know more of you have questions on this, so please call me over if you're stuck. Yeah.
So I know that the second one has one less H,
Mhm.
but where are we getting the NA from?
Just hang on, right?
So that's supposed to be the conjugate base.
That's the conjugate base. So
Okay.
great question here. Second one has one fewer H's, right? So it is the conjugate base. Suddenly there's a sodium there. Shouldn't bother you. Okay. If I go to the shelf, I will never pick up off the shelf anything that's not a neutral compound. All right. So if I have the conjugate base and it has a negative charge on it, there's got to be a counterion in there. If I was to get a bottle full of a bunch of negatives, it'd be like explosive reaction, right? Ton of energy involved in separating charges. You may not have a feel for that. I've never picked up, I don't have a feel for what the bottle would do because it doesn't exist. People can't make it, yes.
So the A, the anion, that is NaSH.
Yeah, NaSH, this is, it's a little confusing because the H's move places, right? But the NaSH is, you could think about it like this. Okay, more obvious that way. Okay, great questions there. See, if you guys don't ask questions, I look at that and I go, yeah, of course that's the conjugate base. And you're like, wait, there's sodium and you move the hydrogens, and I wouldn't even realize that. So I need you to ask questions to help me out there.
So do things ever actually hang out as ions in the solution though?
So the question is, do things hang out as ions in solution? Yes, they hang out as ions surrounded by water, but I can't take, without putting in a lot of energy, I can't take all the plus ions and put them on this side and all the negative ions and put them on this side and then like squirt it out into a different bottle. That takes a lot of energy. And in fact, from a biological sense, cells, what they do, your mitochondria pump it so they have a very slight difference of the amount of ions here compared to here, slight difference in charge, and that's how they fuel making ATP. So slight difference in charge about across the membrane, super useful.
Could you scroll up just for a second? Because I
Yes.
think I copied down.
Scroll up for the, what did I?
We derived for the equation.
Oh, the equation, yeah, I lost you, the Henderson-Hasselbalch equation. There you go.
Okay. I wrote a plus sign, so I was.
Okay. I don't know how much you guys need it, but I'm gonna go ahead and give you one more minute, and then we're gonna move on. This is not
I wrote that. Yeah. Yeah.
Okay, let's go ahead. I'm gonna work this one. All right, I'm gonna make myself room. I'm gonna scoot this all the way to the top, well, so I can see my Ka there. And I do happen to have the Henderson-Hasselbalch equation memorized. It's equal to pKa. Used to be I talked to classes about how I don't memorize this equation because I just could derive it, which is really cool. It's really cool to be able to just derive these things. I always give you the equation, so it's a different system. Okay, so there's our equation right there. As we discussed, this is our conjugate base, and this is our acid, all right? And then what I need is I need to get the pKa. I don't have the pKa, I have the Ka, right? So the pKa is equal to the negative log of the Ka is equal to, well, the negative log of the actual number, which is 8.9 times 10 to the negative 8th, like that. All right, so I'm just going to go ahead and put that in my calculator. 8.9, 8 negative, take the log of that, and I get 7.05. Okay, that's what my pKa is. So now I can just put everything into my equation. My pKa is 7.05 plus the log of my A minus is 0.85 molar over my acid concentration, which is, or my HA, which is 0.5 molar quantity. And so I'm going to go ahead and divide these, take the log, and then add it to that. So 0.85 divided by 0.5 equals, take the log of it, and then add it to 7.05. And I get 7.28 is my pH. Other people get that? Okay, good. So we had a little bit of confusion and a little bit of reasonably or understandable confusion about the sodium and moving the H around. But outside of that, I'm hoping that you see that this was a lot less work than doing an ice table. Okay, it's a lot better than doing an ice table for these things. You could do both. You could do either. And then on a quiz or a test, I don't care which one you do, as long as you A, get the right answer, and B, have enough time to finish the quiz or test, right? Questions? Okay. I'm going to show you something else here, and it's going to be related to what we're about to talk about in our last 10 minutes. So this, compared to the pKa, this is a higher pH, right? And I have more of the conjugate base than I do the acid. So that's going to always be the case. If I have more conjugate base, I'm going to have a higher pH than the pKa. And if I have more acid than the conjugate base, I'm going to have a lower pH. More acid is lower, right? These are relative to the pKa. Super useful in biochemistry when we do that. All right, so let's talk about the ratios of these. We're going to skip these problems. We'll come down here. This is great. I love this picture for explaining this concept. We'll explain it with math in a second. But if we were to take, this is acetic acid. The pKa of acetic acid is 4.76. Okay? When I have equal numbers of the acid and the conjugate base, my pH is equal to my pKa. All right, so I have equal numbers of the protonated and non-protonated form. If, and we'll do the math to show this, if I have 10 times as much base as I have acid, I'm 1 unit higher. Okay? And it's not shown here, but if I had 10 times as much acid as base, I'd be 1 unit lower. It would be 3.76. Okay? If I have 100 times as much base as acid, I'll be 2 units higher, and vice versa. If I had 100 times acid as compared to base, I'd be 2 units lower. Does that make sense? All right, so what we get out of that, I'll talk about what we got out of it, and then we'll prove it with math, is we get out of that a rule, 2 rules actually. Well, maybe I'll make it 1 rule. Buffers work best when you have when the ratio of acid to conjugate base is between 1 to 10, 1 over 10 and 10 to 1. Okay, so in other words, we don't want to ever be far, you don't want to, if you're trying to work with a buffer, you don't want to have those ratios be more out of whack than that. And you know this from what we talked about earlier, that if I have 10 to 1, so let's say we're here, right? Relative to the amount of conjugate base I have, I don't have much acid to buffer in that direction. If I add base, I take away OH minus here, I don't have much of this left to dissociate to go that way. Okay, so that's 1 rule. And the other rule in terms of the pHs is, this is acetic acid, but let's think about a system where we've got, think about your blood, right? Your blood's pH 7.4, all right? I do not want, if I was working with blood, which I did as an undergrad, I don't want to collect blood or get valuable blood from a patient and mess it up by making my solution wrong, all right? So if I'm expecting, if blood is happy, if your blood cells are happy at pH 7.4, they are not going to be happy 2 units away. They're not going to be happy at 9.4 instead. They're going to die. It'll blow up, degrade, I don't know what. And at 7.4, remember that's blood pH, they're not going to be happy at below that, it's 5.4. Okay. Does that make sense? All right. So thinking about, let me do a blood pH thing down here real quick. When we think about you, right? This is you. Okay. These are your lungs. Okay. The pH in your lungs is about, the pH of blood is about 7.6. If you're working out, here are your legs. Down to your legs, the pH of your blood is going to be about 7.2. All right. We can use Le Chatelier's principle to explain that. We can use that bicarbonate buffer system. You're making CO2 in your legs and you're getting rid of it in your lungs. That's how you would explain this. You go up and look at that. I'm not going to do it, but because I want to finish off this ratio thing. Okay, but that's an acceptable range for your blood. Okay, your pH, I think it's pH 6.8 that really you start having problems. Okay, but not a full unit away, not 2 units away. So buffers work best when those ratios are 1 to 10 or 10 to 1 or somewhere there. And what that also means is when buffers work best within 1 pH unit of the pKa. All right, so if you're picking a buffer to use in some experiment, if you were to use this as your buffer, acetic acid and acetate, you could. But whatever experiment you're doing, you want to be doing around pH 5, right? You don't want to be doing it more than 1 unit away from this. Otherwise, pick a different buffer. Pick something with a different pKa. Does that make sense? Okay, so we've got 4 minutes left here. Let's show with math that this is what happens. If I can actually get this down here. Here we go. Okay, so our Henderson-Hasselbalch equation, right? It goes like this. pH is equal to pKa plus the log of A minus over HA. I drew it small there because I'm going to use it below, okay? But the pH is the pKa plus this is a correction factor, right? For how much acid and conjugate base we have. So let's just look at that correction factor. So here I have the log, right, of A minus over HA. My goodness, I either need more coffee or I need less coffee. Not sure which. Okay, so it's that, right? So it's the ratio, right, of those two? If I look at these up here, I have 5 of these and 5 of these. It could be 5 molar and 5 molar. It could be 0.5 molar and 0.5 molar, right? It could be 0.05 and 0.05. They all give me the same ratio. So let's just use the numbers we've got there. So we're doing above, this is for this one. We're going to do the log. We had 5 and 5, right? Put whatever units next to it you want. 5 divided by 5 is 1, right? Put 1 into your calculator and take the log of it. What do you get? 0. Remember that is a correction factor. Okay, I lost my pen. There it is. That's a correction factor there, okay? So 0, so when these are equal, the pH is equal to the pKa. Do you see that? Okay, we've got 2 minutes left. Over here, it would be the log of, it'd be the log of 10 over 1, right? Put 10 in your calculator, divide by 1, 10, take the log of that. What do you get? 1. So that's 1. Remember, this is a correction factor right here. So when I go to that ratio, I add 1. You see that? It's just dropping out of the math. And then finally here, 100 over 1. What's that going to be equal to? 2. So we have a pH that's 2 units higher. Do you see that? Okay. Yes?
Is it like every power of 10 you increase by 1?
Yeah, it's a good observation. For every power of 10, you increase by 1. So if I had 1 to 1,000, it would now be 3. And then when you go the opposite way, the opposite is true. So here we're adding more base than acid, and the other way is more acid than base. Any other questions? Okay, as much as it pains me to do so, at least on my clock, I'm letting you out a minute early.